Alrighty. Okay, so the general characteristics of acids and bases, they're really down here, but acids taste sour. They're mostly in foods and not in cleaning products. pH lower than 7. React with metal. They feel like water. Turn blue litmus paper red. I think that's it. Okay. What are my bases? They taste bitter, although you don't want to taste most bases because they are used in cleaning products. pH greater than 7, so 7 or greater. Turn red litmus paper blue. Blue bitter base. Blue. Oh, helps if you spell it right, Erwin. Blue. Slippery. Slippery. They feel like I don't know if you've ever felt bleach, but it's very, very slippery. Define the following: Arrhenius acid, proton donator. Arrhenius base, hydroxide donator. And the general neutralization equation, and I'll just give an example here of HCl plus NaOH. This is a classic Arrhenius acid and base. Goes to water and a salt, NaCl in this case. Now, Bronsted-Lowry acid, same, H plus donator. Bronsted-Lowry base, H plus acceptor. And that would be like NH3 plus H2O goes to NH4 plus OH minus. So that would be a acid, base, conjugate acid, conjugate base. That's what Bronsted-Lowry gives us, is those conjugates. Okay, taste sour. That's an acid. Change red litmus paper blue. That's a base. Turns phenolphthalein pink. Also a base. Remember, that was NaOH in that burette. Changes blue litmus paper red. That's acids. Reacts with metal. That's acids. Feels slippery. That's base. Tastes bitter. That's base. Feels like water. That's acid. pH greater than 7. That's base. Feels like water again. Acid again. Okay, so that's general characteristics. Vinegar, acid. Alkaline is just another word for base. Lemon juice, acid. pH 3, acid. Bleach, cleaning product, base. pH 7, neutral. Remember, pH 7 is neutral. Ammonia, that's window cleaner, by the way, base. Coffee, acid. NaOH, as soon as you see that hydroxide, you know this is a base. It's an Arrhenius base. Pure water, neutral. All right. Given the formula, HClO4 plus H2O goes to H3O plus ClO4 minus. Choose the correct answer. HClO4. So basically, they're focused on HClO4. So what I recognize here is that this is an acid. And it is both a Bronsted-Lowry acid or an Arrhenius acid, because that is the definition of an acid. Is an example of an Arrhenius acid because a proton is accepted from water. That is not true. Water is not giving me a proton, or it would be a hydroxide on the other side. Is an example of an Arrhenius base? No. An Arrhenius base has an OH group to it. HClO4 is an example of a Bronsted-Lowry base because a proton is accepted. No. If it accepted a proton, it would be H2ClO4 plus on the other side. That is not what occurred. It gave away a hydrogen. HClO4 is an example of a Bronsted-Lowry acid because a proton is donated. Ding, 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 ding. D. Classify each of these compounds as an Arrhenius acid or an Arrhenius base. If it has a hydrogen in front, it's an acid. If it has a hydroxide attached to it, it's a base. Hydroxide, base. Hydrogen, acid. Okay. All right. So the way I do conjugate acids and bases is I block the right side of the equation. And I focus on this side. Either one of these can be an acid because water is amphoteric. It can act as an acid or a base. And HSO4 is amphoteric. It can act as an acid or a base. So what I know is one of these is going to donate a hydrogen. If this donates a hydrogen, it's going to be SO4 2 minus on the other side because it will have one less proton. If this donates a hydrogen ion, both of these hydrogen ion, I should say hydronium, then it's going to be an OH. So let's see what we have. The winner is SO4 2 minus. This thing donated the hydrogen. This is the acid. The other reactant is the base. Acids become conjugate bases. So after it donates a hydrogen, it is SO4 2 minus. That is a conjugate base. And bases become conjugate acids. What is the conjugate acid in the following reaction? It is H3O plus 1. What is the conjugate base in the following reaction? Well, again, I'm just going to cover this up. If this is the acid, I'm going to have Br minus on the other side. If this is the acid, I'm going to have OH minus on the other side. I end up with Br minus on the other side. So this is my acid. This is my base. This is my conjugate base. This is my conjugate acid. What is the conjugate base? The conjugate base is is Br minus, yeah, there we go. That guy, Br minus 1, conjugate base. And here they ask for my conjugate acid. Make sure you get your charges right. If you are adding a plus charge to something, then it has to accept a plus charge. Like this Br minus, if I add a proton, becomes HBr uncharged. That's why it shows that way. Okay, so I'm going to pick the acid out of both of these. If this is the acid, it will be ClO4 minus. If this is the acid, it will be OH minus. Oh, ClO4 minus is my winner. So that's my acid. That's my base. Acids become conjugate bases. Bases become conjugate acids. If this is the acid, I'm going to have HSO3 1 minus. If this is the acid, I'm going to have OH minus. HSO3 minus is the winner. This is the acid. This is the base. This is the conjugate acid. This is the conjugate base. Remember, acids become conjugate bases. Bases become conjugate acids. You can always follow the anion around and see who did what. SO3, SO3, acid, conjugate base. What are the conjugate bases for the following acids? So I'm removing a plus charge. So if I remove a plus charge from a ClO4, an HClO4, that is going to become ClO4 minus, because now it's going to have one extra electron, one less proton. H2O is going to become OH minus. You just have to think, after it donates the hydrogen, it turns into a conjugate base. What are the conjugate acids for the following bases? Well, now we're going to gain a hydrogen or a hydrogen ion. So now we're going to gain a proton. So we're going to have HCN, and that has no charge because we're adding a plus and a minus together. This will come H3O and has to have a plus charge because it was neutral before I added the proton on. Don't forget, when you add a proton, it changes the charges of things, or when you subtract a proton. What is the conjugate acid of CO3 2 minus? Well, all I have to do is add a hydrogen to that. So if this is my base, then it's going to gain a hydrogen and become a conjugate acid. And that conjugate acid is going to be HCO3 1 minus, or this thing right here. That is going to be my conjugate acid. This is my acid. This is my base. Bases become conjugate acids. Acids become conjugate bases after they give away their hydrogen, hydronium ion. What is the conjugate base of NH4 1+? So if that's my acid, then my base is going to have one less proton. It's going to be NH3, and it's going to lose a plus charge. So I'm going to become NH3 neutral, which is going to be C here, NH3 neutral. Identify acids, bases, conjugate acids, and conjugate bases. Again, if this is my acid, I'm going to have PO4 3- on the other side. I do not have that. If this is my acid, I'm going to have OH on the other side. I have that. This is my acid. This is my base. This is my conjugate acid. This is my conjugate base. Remember, it has to make a salt and water to be a neutralization reaction. Just because it has water in the beginning does not mean it makes water and a salt. This did not make water and a salt. That would be Arrhenius. All right. If this is my acid, I'm going to have HCO3-. Oh, I see it. That means that's my base. That's my acid. That's my base. This is my conjugate base, and this is my conjugate acids. Bases become conjugate acids. Acids become conjugate bases. Follow the anion. CO3, CO3. NH3, NH4. What are the conjugate bases for the following acids? Okay, so you're giving away a hydrogen and losing a plus charge. This becomes NH3. Conjugate base for this, the giving away a proton, which means I'm giving away a plus charge, CO3 2-. It's already minus. Now I'm taking away a proton, so I'm making it 2-. What are the conjugate acids for the following bases? Okay, I have a -2 on an SO4. Now it is HSO4-. I added a proton. And here I have HCO3-, H2CO3, and now it's neutral because I added a plus charge to it. Okie dokie. What does the term amphoteric mean? Can act as an acid or a base. And all you have to do is turn back one page and you can see water acting as an acid. And where's water acting as a base? Water acting as a base. If it acts as a base, it accepts a proton. If it acts as an acid, it loses a proton or hydronium ion. So the best example, water. But there's another one on the back, HSO4-. If you need another one, that can accept a proton and become H2SO4, or lose this last proton and become SO4 2-. How can one determine if an acid or base is strong? 3 examples. Okay, pH. That's going to be my first example. If you have a pH probe and you test the pH and it is 0 to 1, that is a strong acid. Dissociation. If it dissociates 100%, it's a strong acid or a strong base. If it dissociates any less than 100%, then it is a weak acid or a weak base. And let's see, conductivity. Strong acids dissociate 100%, so if I put a light bulb connected to a battery and some wires in a beaker of a strong acid and a weak acid, the strong acid is going to glow very bright because it's going to conduct all the electricity. A weak acid is going to not be very bright because it's not going to conduct all the electricity. There's other ways that we can test acids and bases. What is pH? pH is power of hydrogen. That's not really what it means, but that's what I'm going to lie to you and tell you it means. The potential of hydrogen, there's been a lot of stuff where they've said what this means, but the guy who wrote it in his logbook wrote potens hydrogen in one place, and that little p means negative log of. So if you're telling me that that's the power of hydrogen, then pK, which pKa, which exists in AP Chem, is the power of, oh no, that's a dissociation factor. So power of hydrogen is what I'm going to tell you right now. And then in AP Chem, I'll tell you something different. What pH values determine whether a substance is acidic, neutral, or basic? Okay, acidic, pH less than 7. Neutral, pH 7. Basic, pH greater than 7. So what does that mean? That means a strongest base would have pH 14. Strongest base. Strongest acid would have pH 0. Remember, we use the pH scale to determine the strength of or whether it is an acid or base. Do not use pOH. What is pOH? How does it relate to pH? pH plus pOH equals 14. pOH is equal to the negative log of the concentration of hydroxide ion. So you can call it, power of hydroxide, I guess, but that's not it. And pH is equal to the negative log of concentration of hydronium ion. So that's what pH and pOH are and how you get from one to the other. If we use this formula, pH plus pOH equals 14. Acids with a low pH are strong acids, while bases with a high pH, just what I said before. pH 14, strong base. pH of 0, strong acid. Which of the following pHs would be the strongest acid? Lowest pH wins. This is 100 times stronger than this, which is 1,000 times, wait, 3, 4, that's 10, 100, 1,000, yeah, 1,000 times stronger than pH 6. Which of these pHs would be the strongest base? pH 13 would be the strongest base. A solution has a pH of 4, while solution B has a pH of 6. Which solution is more acidic? Solution A, the lower pH is the stronger acid. What is the pH of a solution with a pOH of 9.5? 14 minus 9.5 equals 3.5, right? Yeah. So that is my pH. Remember, 14 minus pH is pOH, or 14 minus pOH is pH, your choice. Sodium hydroxide has a pH of 14 and baking soda has a pH of 9. So sodium hydroxide is a stronger. So sodium hydroxide is stronger base. I would like it to say base somewhere in here, but it doesn't. So whatever. Coffee has a pH of 4 and stomach has a pH of 1. Coffee is a weaker acid, weaker than stomach acid. Yeah. Solution A has a pH of 2, while solution B has a pH of 5. Which solution is more acidic? Solution A is more acidic, and since it is 3 steps away from that, it is 10, 100, 1,000 times stronger than a pH 5 solution. It is 10 times stronger between each step of the pH. What is the pH of a solution with a pOH of 7.6? 14 minus 7.6 equals, what is that, 6.4? Is that my pH? Yeah, 6.4. 4, 10, 7, 14. Yeah, that's it. Whew. I'm mathing without a calculator. You should be scared, guys. Be very scared. Okay, where are we at? 1839. We can keep going. What is a neutralization reaction? Does it contain Bronsted-Lowry or Arrhenius? Well, we know this is conjugates. And conjugates don't make water in a salt. But we know this is a hydroxide, and we know that that's going to make waters in a salt. So what is a neutralization reaction? It is a strong acid plus a strong base make water and a salt. And sometimes, quite literally, salt that you use to salt your fries with. How does water form from the acid and base in neutralization? Well, if I just take the ions of this and this, because we know it dissociates 100%, this is strong, strong. So the ions are this plus this. Well, I don't care about these two. They don't do anything for me, but H plus and OH minus combine to make water. That is how you make water from an acid and a base neutralization. What is a titration? It is a tool used to determine equivalent moles of acid and base. And when is it used? To get molarity of unknown solutions. For instance, you had an unknown molarity acid that you did a titration with, on Monday? That we determined the moles of my base used, and then we plugged it into the molarity formula, and we got a molarity for my acid, the strength of my acid. What are acid-base indicators? Litmus paper, blue and red, phenolphthalein. And what are some uses for them? They turn color in an acid or a base. That's what indicators do. So I use blue litmus paper when I'm testing an acid, and if it turns it red, then I know I'm dealing with an acid. Usually you take a piece of each. Like if I had an unknown fluid, beaker of some substance, and I wanted to know whether it was acidic or basic, I would take a red piece of litmus and a blue piece of litmus. I'd stick them both in there and see which one turns colors. If it's blue and it turns red, it's an acid. If it's red and it turns blue, it's a base. What is the general equation for a neutralization reaction? Acid plus base goes to salt plus water. We can do HCl plus NaOH goes to NaCl plus H2O. They're always going to make a salt and water. And this is all only Arrhenius. Arrhenius is neutralizations. The other ones are Bronsted-Lowry. What would you use to clean a strong acid? Strong base. Why? Because I'm just going to make salt water on my floor. Salt water, not dangerous. Not dangerous. So easy peasy, lemon squeezy. How could you determine if a substance was an acid or a base? I could use litmus paper, exactly like I said. If I had a beaker full of liquid, I would take some red and blue litmus paper, I'd stick it in there and see which one turned colors. That would tell me if I had an acid or a base. What equation is used to solve titration problems? Ma times Va equals MB, molarity, times volume of base. And if you use milliliters, you can use milliliters on both sides. If you use liters on one side, then you have to use liters on the other. If you use milliliters on one side, then you have to use milliliters on the other. But, so we're going to go right into some of these problems here. The numbers that are beside each other are going to go in one side or the other. And here it's a hydroxide, so this is base. So what I have is a volume of base, 43.55 milliliters of potassium KOH. And I have a molarity for my KOH, 0.030 molar. And then I'm going to set that equal. And I'm going to neutralize 20 milliliters of X molar acid. This is how we determine the molarity of an unknown acid. It took me this many milliliters of base. I know the molarity of my base, and I had 20 milliliters of my acid, so now I just have to do a calculation. 0.30 times 43.55 enter divided by 20 milliliters is X equals 0.65 molar. What am I dealing with? Acid, nitric acid, HNO3. That is the concentration of my nitric acid, and I just use MAVA, MBVB. Same thing I'm going to do down here. Down here, the two numbers closest to each other, and these are acid this time, so I'm going to put them on this side. I have a 2 molar HCl, and I have 85 milliliters of it. And I'm going to set that equal to 100 milliliters of my unknown molarity base. So then I'm going to type in, there's a decimal place there, so don't get lost in that. It's 2 molar, 2.0 molar. 2 times 85, which is 170, and then I'm going to divide by 100 to get X by itself. Divided by 100 equals 1.7. X equals 1.7 molar HCl, base. Now, this is a base that base. What base? Unknown base, so base. We know we have 1.7 molar base, whatever base it is. And again, the numbers beside each other go on the same side of the equation. They're an Arrhenius base, so they are the base side. So I have 2.5 molar NaOH. I have 28.3 milliliters of NaOH. Set that equal, and I originally started with 45 milliliters of my acid, X molarity for my acid. So 2.5 times 28.3 entered divided by 45 milliliters is 1.57. 1.57 molar HCl. Unknown base, nitric acid. Carrying on. We are now at 26 minutes and 30 seconds. Oh man, more of these? All right, we're going to rush through these a little bit. So I have 49.90 milliliters of 0.55 molar HCl equals 25.0 milliliters times X molar. 49.9 times 0.55 entered divided by 25 is 1.09. X equals 1.09 molar. What volume? Okay, 33.3 milliliters times 0.113 molar equals 0.50 molar times X milliliters. They're asking me a milliliters question. Doesn't matter. 33.3 times 0.113 enter divided by 0.5 enter gives me 7.52. X equals 7.52 milliliters of KOH. Solution of 50 milliliters potassium hydroxide requires 35. The numbers that are beside each other are my acids, so 35.2 milliliters times 1.50 molar HF, or hydrofluoric acid, equals 50.0 milliliters times X molarity, my base. 35.2 times 1.50 enter divided by 50 enter is 1.056. X equals 1.056 molar KOH solution. So far, so good. What are binary acids? Acids that contain 2 elements. What are oxyacids? Acids that have polyatomic ions, which are on the back of your periodic table. Ions. What are the rules for naming acids? Okay, ates turn into ics. Ites turn into OUSs. And binary hydro, whatever the second element is, add an ic acid. Example, hydrochloric acid, hydrochloric, bromic, iodic, fluoric. All of those are binary acids. Also sulfuric, H2S, hydrosulfuric acid, H2S, or hydronitric acid, which is the H3N. All of those are binary because they contain 2 elements. Name the following compounds. So I need a periodic table with a polyatomic ions on the back so I can point some stuff out. This is more than 3. If it's 2 elements, sorry, more than 2 elements. If it's more than 2, I got to look at the back. And if I look at CLO, I have hypochlorite. Hypochlorite, hypochlor, and ites turn to us acid, hypochlorous acid. SO4, again, not a binary acid. SO4 group is a sulfate right here. Sulfates turn into sulfuric acid. Eights turn to ic, ites turn to OUS. Binaries are hydro whatever ic acid. Naming bases is really easy. It's the name the first thing and then hydroxide. Iron hydroxide. Okay, CrO4 group. That's more than 2 elements, so I'm going to look for a CrO4. There it is. It is a chromate. That means that this is a chromic acid. Chromates turn to chromic. Write the formula for the following compounds. This doesn't say hydrocarbonic or anything like that. It says carbonic. ICs come from H, so I need to know what a carbonate is. Carbonate is CO3 2 minus. CO3, and it is 2 minus. That means I need 2 hydrogens to balance this thing, to make it balance for charge. So remember, whatever your minus is, you're going to have that number of hydrogens attached to that thing. Magnesium hydroxide, MgOH, and I know that magnesium is +2, that these are -1. You can see that on the back of hydroxide, OH, -1. Therefore, I have MgOH2. Hydrosulfuric acid. Oh, so this is a binary acid, binary hydro blank. So that means that I have H and I have S. S is -2. That means I need 2 hydrogens for this thing, H2S. Bromous acid. Bromous, OUSs, come from ITEs. So I need to find a bromite. Bromite is right here, BrO2 -1. So I'm only going to need 1 hydrogen. Hydrogen, BrO2. Bromous acid. Okay. Oh, a little bit more naming, and we're done. Or formulas. Name the following compounds. As soon as you see that hydroxide, you know this is potassium hydroxide. Okay, next we have a binary acid, and we know that binary acids are hydro, whatever this is, ic acid. This is hydrobromic acid. Hydrobromic acid, just like hydrochloric, hydrofluoric, hydrosulfuric, hydronitric, hydro, whatever you want to say. As long as it has 2 elements, it's hydro something. C2H3O2. So if I look on the back, I see an acetate. Acetates, eights become ics, so this is acetic acid. Acetates become acetic. Eights become ics. PO3 group. A PO3 group, that's going to be a phosphite. PO3s are phosphite. They are charged -3. That means H3PO3. Oh, sorry. Wait. Phosphite, that means phosphorus. Forgot which way we were going here. Phosphorus acid. Ites become oses. I wasn't looking for a formula. Write the formula for the following compounds. Nitric acid. So X come from eights. So I need a nitrate. NO3, and it's -1. So HNO3. You can see that nitrate right here. NO3, charge -1. That means I need 1 hydrogen for it. Chromium hydroxide. CrOH2. How do I know that's 2? Because this is 2. +2. It's transition metal, CrOH2. Hydroiodic acid. Oh, thanks for giving me an easy one. If you see hydro, then you know it's a binary. Now, that is not hypo. You see that there's a lot of hypo things in here. Hypo things are determined, like if that's an ite, it turns to OUS. Ite, all OUSs. Hypoiodous, hypochlorous, hypobromous acids. Okay, phosphoric. Again, there's no hydro, so it's an ic ending. It came from a phosphate. Phosphate, PO4 group -3. That means H3PO4 is my phosphoric acid. That is the sum total of the review for acids and bases. The only other thing you have to do is you have to remember how to do a chart like this. You're going to have all the formulas. It's never a problem. If they give you a concentration, it is negative log of that concentration gives me pH. So if I take negative log, let's clear all this out. Negative log of 5 times 10 to the negative 2, 5 times 10 to the negative 2, then I have pH, 1.30. And if I have pH, then I have POH, because 14 minus 1.30 is 12.7. And if I have POH, then I can take POH, I can take 10 to the negative POH, and that will give me hydroxide concentration. 10 to the power of negative 12.7 is 1.99 times 10 to the negative 13th. 1.99 times 10 to the negative 13th. Acid or base? Always based on pH. Lower than 7, acid. Higher than 7, base. Higher than 7, base. Higher than 7, base. Higher than 7, base. Lower than 7, acid. Lower than 7, acid. Lower than 7, acid. Now, when you're given a POH, again, it's just 10 to that power. And hopefully, let's see. So if I'm given a POH, 10 to the negative POH gives me the hydroxide concentration, just like 10 to the negative pH gives me the hydronium concentration. So if you give me a pH or you give me a POH, I can give you the concentrations. So, which one did I want to do? I want to do this one. POH of 4.1. 10 to the negative 4.1 power is 7.9 times 10 to the negative fifth, and you can make that into scientific notation. All you have to do is do mode, scientific, second quit, enter, 7.94 times 10 to the negative fifth, 7.94 times 10 to the negative fifth. And I know what pH is, because pH plus POH equals 14. So 14 minus 4.1 is 9.9. pH is 9.9. If I take 10 to the negative 9.9 power, I get the concentration of the hydronium ion. 1.25 times 10 to the negative 10th. And if I look at pH of 9.9, that is a base. Anyway, I'm going to let you practice that sheet the rest of the way. I've already given you the key for the top, so if you need a key for the top, there's the key for the top. And if you have any questions, come into class early tomorrow or come after school today, and I will answer them. All righty. Y'all have a fantastic day, and I will see you when we test tomorrow.